Again, it's my pleasure to introduce Bob Clark, Senior Research Fellow at Simulations Plus. Bob, I think there's a little special event today in the honor of Bob, who's been with us with many years and has contributed in so many ways in the models that are found throughout our software. So Bob, thank you so much for your contribution, and the floor is yours.
Okay. You see my screen okay?
I can see your screen. Yep.
Does it look like the right one?
Yeah, I'm going to stop my video and you're free to have yours on.
Yeah.
And I'm going to mute myself as well.
Okay. Except I'm seeing your screen, not mine. Eric?
Yes.
I'm seeing your screen, not mine.
I'm not sharing my screen. I'm not sharing
you
my
see
screen.
my screen?
I see your screen, model, how we built and validate industrial strength models.
Okay.
Yeah.
Okay.
So, yep.
Okay, I will try to, let's see if I do this. That's interesting. Okay, well, I'll just go with it. Okay, I'm Bob Clark. I'm here to talk today about how we build and validate the industrial strength models that we provide in ADMET Predictor. They're built primarily in ADMET Modeler. Now, what does a good model look like? I like to think of our QSAR models as bridges. And when I think of bridges, this is the one that comes to my mind, the Mackinac Bridge, which links the upper and lower peninsulas of Michigan, which is where I grew up. Now, like good bridges, good models share common structural elements and are built using similar techniques, but each one is unique because each endpoint is unique. Each one is also a good, strong, reliable tool tailored to the particular demands of the relevant endpoint. It will get you and your project from where you are to where you need to be safely, reliably, and efficiently. Now, what are the elements of a good model? Good data subjected to thorough curation, discriminating broadly applicable descriptors, a robust machine learning engine, good validation tools carefully applied, and reliable ways to estimate predictive uncertainty. First, I'll talk about getting good data and subjecting it to good curation. Now, the literature is a lot like a river. The data in it change constantly in quantity and quality. Now here I tend to picture the Mississippi River as it runs past St. Louis, Missouri, where I spent 25 years, about 2/3 of my professional life to date. And the second point about the literature being like a river is it often contains a lot of distracting things that do not really belong there. So does the Mississippi River. You can think of discarded tires and dead cats. Because of that, it usually needs to be cleaned up quite a bit before you want to use what comes out of it. And the last 10% of cleanup takes at least 90% of the effort. So we spend a lot of our time cleaning up the data in order to clean up that last 10% to make it industrial strength data. Because you need industrial strength data if you're going to have an industrial strength model. Now, this is all you have to worry about if you're lucky in your choice of endpoint. If you're not lucky in your choice of endpoint, then the literature also can look an awful lot like a swamp. I say that because instead of being a nice even flow, even distribution of data, it often comes in big clumps of results for analogs that have been disclosed together, all in a single paper. And this can and does lead to non-random errors, i.e. systematic biases. Now, data compilations are great, but they can easily introduce errors. Unfortunately, they rarely remove them. And that's as true for literature reviews as for public and commercial databases. Now, the compilations are convenient, but counting on someone else to have fully curated the data for you can be and often is a costly mistake. For a detailed discussion, see Fiofio Zin's talk later today on Untold Stories of Data Curation. It'll be at 2:45 Eastern, 12:45 Pacific time, about 2 hours from now. Now, how do we process the data? We collect it from diverse sources with consistent endpoints. Here we have to strike a balance between diversity and consistency. Academics and many in industry have the luxury of choosing artificially but arbitrarily uniform assay conditions. We don't have that luxury. Our models have to be as broadly applicable as possible while still being robust, because the people who want to use them and the conditions in which they want to apply them are range across quite a range of conditions. We reconcile redundant entries and take median values. Now, redundancies in the data are very useful. They establish experimental error ranges, and more importantly, they help identify errors in the data. Medians are nice because they are more resistant to bias than the averages are. We then standardize the data in terms of structures, units, and so forth, and analyze them graphically for distribution, and then we model them. Then we inspect the outliers to find systematic errors. Now, outliers are critically important way to highlight biases and to spur investigation, not just grounds for excluding observations. You should probably be worried if you do not see any outliers. And we build more models, re-inspect for new or less egregious outliers. And we iterate that until the outliers are inexplicable or they're gone. Now, this is a recent example of curation from it that we ran into in working on some transporter substrates. The one on the left comes from Kemble. The one on the right comes from a commercial database. Now, they look like a really nicely matched molecular pair. That seems unlikely, however, because even though they come from different papers, they have identical transport rates, 210 nanometers per second. Not only that, but there are actually 8 pairs, all of which have paired molecular transport rates. And this happened because the ones on the left are all wrong. Now, if we had not caught this, we would have been feeding the model wrong information. And two things can happen if you do that. Either the model will be flawed, or the model will give you the correct answer for the wrong reason, which means that down the road, it will have learned biases and will give you wrong predictions in other circumstances. Next, I'm going to talk about discriminating and broadly applicable descriptors that we use. The 2D molecular descriptors work well for most of the ADMET properties that we model. 3D descriptors tend to overspecify a particular conformation without adding much value for ADMET properties. That's partly because binding sites for ADMET properties either don't exist, for example, pKa and solubility, or the sites are too flexible and promiscuous to use docking tools. Examples of that are SIPs and UGTs. We also avoid simple structure-based descriptors because they tend to be too localized and too specific and restrict the domain of applicability. Unusual combinations of atoms do sometimes have unusual properties, but usually they don't. Whereas interactions between overlapping fragments in terms of the effect that they have on the properties are easily underestimated if you're using fingerprints alone. We focus on topological indices, electrotopological state, charge-based, and ionization descriptors based on pKa analysis. As if you caught David's talk, he mentioned the fact that our pKa model finished at the top of the sample 6 pKa prediction competition that just was published in JCAMD. And finally, initial selection is filtered based on the extent of variance of each descriptor, as well as pairwise and multi-way covariance. Now, unfortunately, most other software from other companies does not take multi-way correlation into account. Now, what makes a good model? Now I'm going to talk about the machine learning engine and the validation tools we employ. And those I'll talk about together because they're pretty intertwined mechanistically. We use artificial neural network ensembles with a single hidden layer of neurons. They usually work very well for single task ADMET modeling. We have explored deeper neural networks as well, as has been reported in the more carefully conducted analyses, and as is expected based on theoretical considerations, deeper networks do not generally confer any substantial advantage for single task problems when sophisticated enough descriptors are used. When we do need alternatives to the artificial neural networks, we have support vector machines, multiple linear regression, and partial least squares analysis available to us if we need them. Each model in the ensemble is trained on an independent random about 2 to 3 training pool split into train and verify sets. You can think of this as a sort of deep cross-validation if you want. And performance on the verify subset is used to stop weight optimization before a model can become overtrained. And multiple architectures are examined and the best performing one is kept. Now, actually, multiple performance criteria are used, which now includes the quality of the uncertainty distributions, which I'll talk about in just a moment. Again, I refer you to the Clark and Daga publication cited above for details. This is an overview of how our ANNE models get built. We collect structures and experimental data, compute descriptors, then we remove the low variance and highly correlated descriptors. Select a test set, and we have several methods for doing that. We tend now to generally use stratified sampling. For small data sets, Cahonan maps give a little better performance. But we also have k-means and manual test set selection. We rarely use strictly random test set selection. We split it out, sequester a test set, and then take the training pool and split out several folds, each with its own split between proper training set and verify set. Again, about 2 to 3 proportion, about 60% in the proper training set, and generate a grid of artificial neural networks where each cell in the grid is an ensemble. And the grid is laid out in terms of K descriptors by M neurons. And we look for patterns of performance as much as individual performance. That is, if there's one particular ensemble that sticks out as being spectacularly good, that's probably accidental. And so we'll also try using different random numbers to seed the initial weights in order to make sure it's not just an accidentally good model. And that after all that is done, we end up with the best model we've selected and use that ensemble of artificial neural networks to be our commercial model. This is a model of the artificial neural network itself, laid out. We have a stack of inputs. Each of those inputs, it's a fully connected neural network, so each input is connected to each of the hidden neurons and a single layer of hidden neurons that are connected to an output neuron. An arctangent function is used to merge the inputs from each of the input neurons for each intermediate neuron. And then a logistic function is used to merge the inputs from the hidden neurons to the output neuron. The objective function is this complex thing here, which is basically the C is an indicator function, tell you whether the observation is a ground truth, is a positive or negative observation. Each starts from a set of initially randomized weights. And I need to apologize to you and to our marketing and sales staff for not being able to figure out how to recolor the equations so that they would be white on a black background. Microsoft's current equation editor doesn't seem to make that possible. And the last thing I'll talk about quite briefly is the ways to estimate predictive uncertainty. Now, I could have inserted a lot of equations here, or worse, I could have inserted a lot of statistics. But in this final section, I restrained myself. Instead, I went for the next best thing, an XKCD cartoon. And I'll read it to you real quickly. The first fellow says, "This is your machine learning system?" And the other fellow replies, "Yep. You pour the data into this big pile of linear algebra and collect the answers on the other side." So the first person says, "But what if the answers are wrong?" And the second fellow, sitting on top of the pile of very messy pile of data, says, "You just stir the pile until they start looking right." Now, I hope I have convinced you that our model building system is more systematic and robust than this cartoon would suggest. Regardless, we realized a couple of years ago, as did some other groups, that if you stir the pile enough times and keep track carefully enough of how often your past predictions were right, you can estimate going forward how confident you should be in the accuracy of your future predictions. Now, variability and ensemble predictions is related to uncertainty, but not directly because the models are not statistically independent. And what it follows from, it turns out that the predictive errors follow over-dispersed distributions. That's a subtle but an important statistical point. Other groups working in this area have looked at using variability and ensemble predictions as a descriptor for modeling average uncertainty. But we looked at it as a statistic that can tell us what range of uncertainty to expect, which is a subtle but fundamentally different perspective on things and gives you some fundamentally different answers. For uncertainties in predicted classifications, we've shown that the observed errors follow a beta binomial distribution, and we published that several years ago in Chem Informatics. For regression uncertainty, the joint distribution of the predictive standard error and the standard deviation of the prediction fit, and the standard deviation of prediction fit a pair of coupled generalized gamma distributions. Now, this methodology has been included in Admit Predictor for a couple of years now. And the most recent description was put together. It was an excellent slide presentation from Marv Waldman that he presented at the fall ACS in 2019, titled "A New Approach to Regression Uncertainty Analysis and Applications to Drug Design." It's available on the Simulations Plus website, and I'll be working on a manuscript to publish about this in the near future. There are a lot of people who have worked in this area, including Marvin, Deshwan Zhang, Robert Frenchkovich, Winkle Liang, David Miller, Pankaj Daga, Phil Zin. Whoops, I lost a Phil, sorry. Phil Zin, Mike Lawless, Ola Mikos, and Eric Jamois, most recent addition to the crew, aside from Phil Zin, who's a postdoc. And with that, it's time to go to question and answer session. And I always have to start with the answer to the life, the universe, and everything, which is, of course, 42. But if you have any more specific questions, I can maybe answer them now, or you can send them to me at bob@simulationsplus.com, or as David mentioned, info@simulationsplus.com. And with that, I hand it back to Eric.
All right. Well, thank you, Bob, for this very nice presentation. I don't see any questions in the chat. And I'm now going to the Q&A tab, and I don't see any either. So I think you probably gave us sufficient information that it's all self-contained and nice. If there's more, if anyone has a question now that they did not communicate neither through the chat nor through the Q&A pane, feel free to raise your hand and ask your question. We have a couple more minutes in the session that we can sustain a few questions. Let me show the participants.
I apologize for not having enough experience with Zoom to figure out how I could be looking at you while I was speaking. My apologies.
That's all good. All right. All right. Well, I'm still looking at the pane to see if anything comes up, but I don't see. Oh, Michael. Well, law. I don't see the question on the. I said, Michael Lawless. What was his question? I don't see the question. Q&A. Oh, it's in the Q&A. Let's see. Oh, yes. What is the best statistics to judge a regression model? That's the question from Michael.
The one we look at first is the root mean square error, the RMSE. But we look at that across the test and training and verify, especially to make sure that the verify and the test set are pretty close to each other. And then we also what we call the root mean square uncertainty, which is the confidence model estimation of the RMSE, also needs to jibe with that. And so it's a sort of a single criterion, but it's multi-dimensional. So it's a couple different dimensions of the RMSE.
Yep. Okay. Yeah. I guess I'll add, Bob, that in the AdMet predictor documentation and probably other documentations about our software, we publish pretty religiously all the statistics that's associated to the models for both the training set and the test set. And I think it's really important from an expectation standpoint, because you mentioned RMSE. I mean, if you take 10 to the power of that, then you get a sense of sort of the full difference that you can expect between your experimental values that you may get later and what you predicted through the models. So I think that's very important to pay pretty close attention to those metrics, so that you tune your expectations to what is reported, and then also you use that as a benchmark if you want to better these models, adding data, for example.
Yep. And the uncertainty we provide is, as far as we can tell, is a true estimate, is the estimate of a true standard error of prediction. And as far as we know, we're unique in doing that.
Yeah. Okay. I'm just looking. I'm still monitoring the chat box to see if there's anything more there, but I don't. So, Brian Mathis wants to know if there are any Oh, do we have any dog values from AdMed Predictor that can be used directly in a veterinarian setting? Dog values. I'll let you answer that one. I think I know, but
we don't have any that I know of. Actually, we'd have to consult with the gastro people to know which AdMet properties, apart from solubility and so forth, which you would have to adjust for the pHs of gut and dog intestine and so forth. But I don't, so probably about half of them are relevant to dogs, as long as you take into context the differences in things like pH.
I think the question was more related to the things like blood to plasma ratio, FUP, clearance, the models that they added for rat recently.
Yes. We do not have any dog specific models that I know
of. Not in AdMed anyway. Yeah.
No.
Okay, well, just very well. Yep. The dog clearance and dog FUP, but again, there's no such models in AdMed, at least that I can't speak for GastroPlus, but for AdMed, there wouldn't be. All right. Well,
you could, if you have the data, you could build your own.
Yeah, for sure. Yeah.
That's true. I didn't mention that. These tools, the tools I'm using, and the information you need to use them, the tools are all in AdMet Modeler, which you can buy as part of AdMet, the module in AdMet Predictor, and the documentation I think is really good.
All right. Well, thank you, Bob. I think we're going to close this session and transition to the next one.
Okay.
Thank you so much.
Adieu.